Hello, everybody.
And thank you for coming today. It's a great pleasure today to have with us Professor Prashant Valluri. Prashant is a professor of chemical engineering at the University of Edinburgh, and he works on multi-phase flows, complex multi-phase flows, all sorts of very interesting hydrodynamic stability and droplets. And I believe he also worked on the Jerris code at some point.
Yes.
Yeah, and Prash is a graduate of Imperial College. He got his PhD in the Department of Chemical Engineering at Imperial with Omar. So it's great to welcome you back, Prash. The cat's in the way, but I know the title is Confessions of Droplets and things, but the cat's in the way and I can't read it. So
don't worry.
All to you.
Yeah, thanks a lot. Thanks a lot, Dimitrios, for the invitation. I mean, Imperial is like my home actually, because as you said, I did my PhD there with Omar and Jeff, and I have got a long history of collaboration with them, with you guys. So normally it's almost like going back home and telling your work to your parents and your family and things. So I don't feel any alien to Imperial at all. In fact, it's really an honor to come back to Imperial or present in this way. So yes, so it's not about the cat today, but it's about what the cat is doing today. So the cat is actually watching the paint dry, and probably it's not bored because it knows something more than we do. So my objective, well, our objective, collective objective, is to find out what exactly happens when you have a liquid system which is having multiple components, some of them being more volatile than the other, and some of them may have particles and things like that. What happens? What really happens? So basically, so sorry for the long author list. Basically, it's a tribute to my students as well over the years. So the first, Katie Thompson and Andrew Boyd, they are very, very recent students. But those in green, they are the ones who have graduated. And it's some of their work, which I'm going to be presenting as well, in comparison to some of the new work which we have done. Of course, I've had a long-standing collaboration with Alex Ray, who's now in Strathclyde, as well as George Karapetsas. And both Alex Ray and George Karapetsas are Imperial products. So there's a very strong community out there beyond Imperial as well. So, and of course, Omar, there is a lot of experimental input from Jungo Kim from Maryland and Kelel Safian as well, my colleague at Edinburgh. So they have helped us do some experiments and really verify what we are really doing, whether they're making any sense or not. So essentially within my group, we actually start with modeling, and if we find something really, really fascinating, we then do an experiment to see if our predictions are not fake news, or to prove that hopefully they're not fake news. And of course, I worked a lot with, as you already mentioned, with Stefan Popene and Stefan Zaleski in developing another aspect of Jerris code, and Rama Govindarajan to develop the theoretical aspect. I'll come to that shortly in terms of particles. So the whole story goes around about sessile droplets. So basically, droplets, spherical droplets are rather rare. Any droplet you see, you would have all kinds of weird shapes to it. All of these sessile droplets, and even if they are terribly spherical, or even if they are completely symmetric, so as to speak, they exhibit some massively non-symmetric phenomena. So as you can see from these experiments from my colleague here, Kelel Safian, so you can see that you've got so the first image, I don't know if you can see my mouse pointer. Can you see my mouse pointer?
Yes, yeah, we can.
So this one shows the thermal, this is a thermal image camera as a droplet of ethanol is evaporating. So you can see that you've got these fascinating thermal patterns, which are completely non-axis symmetric. And you find that actually these guys actually rotate all over the place. So they have these fascinating dynamics. And of course, this is a droplet of blood actually as it evaporates. And blood is highly multi-component, and obviously as it deposits, it has a completely non-symmetric pattern. So we did some of the work earlier. And especially for non-spherical droplets and pure droplets, but non-spherical. And we could find that you got these vertical azimuthal currents which go all around the droplet. So this was done through DNS. So this was a long time ago in 2015, which Pedro's work. So one of the outputs we could see from there is definitely that you got a breakage of symmetry. Okay, so initially the droplet the dynamics may look terribly symmetric, but then soon you will evolve into a situation where they're no longer symmetric. And so basically many of the people, initially we would all rely on axisymmetric simulations, but of course we cannot rely on them as much because symmetry is actually broken by the time things are really, it's showing any dynamics and things like that. So basically this was about self-emergence of these azimuthal currents within a droplet. And this is just a pure droplet and supposedly initially symmetric, as you would see. So how do we do this? So we have a host of DNS solvers. So we have TPLS, which we have, the version 3 of that is now open sourced was open sourced in May 2018, and it has a really rich history. And at this point, I'd like to take a little bit of a break and give tribute to Professor Peter Spelt, who I worked with as a postdoc, along with Omar as well. And that was the time we really started making, developing TPLS. And obviously, unfortunately, last year, he passed away. So I just wanted to acknowledge him in this way now. And obviously, when we started working on all these codes, it was 2004, between 2004 and 2008. So access to parallelism was just new at the time. So we were really excited to have access to 4 cores in our machine and basically able to do OpenMP parallelization. And slowly we have migrated to MPI, and now we have highly parallelized structures. So it's started from that point at Imperial, and finally it has developed into a pretty robust solvers, which can be used for all kinds of applications, stratified flows, slug flows, falling films, etc. And we are using it for phase change, as you have seen as well. Quite recently, we have worked on JERIS to develop an immersed boundary framework to actually look at what particles might do. I'll come to that very soon. So just talking about phase change. As I mentioned, we have done some work in terms of sessile droplets, in terms of 3D modeling, in terms of DNS. Both the vapor phase as well as the liquid phase were accounted for. You could see a lot of convection currents going on within the vapor phase. And so that really gave us a lot of food for thought. Then we also looked at different shapes of these droplets in these Nature Communications articles, and how can they, what fascinating features do they present if you have weird shapes, if you have a star-shaped droplet, or if you have a kind of a kidney-shaped droplet, and so on. So all of the work was done there. The next step of the work which we wanted to do was when we really look at any kind of a fluid, especially used in industry, it could be for microelectron, it could be a coolant or something. And most of these are mixtures, and they have got these. And when you have a mixture, you always have this competition between the evaporation or the volatilities between these mixtures. And that is something which we wanted to really understand a bit better. So here I'm showing you in the bottom, I'm showing you an experiment by one of my students, Adam. It's a spherical, it's basically a hemispherical droplet, ethanol water, 25% ethanol. And what he's just doing is he's just showing the IR photograph. And you can see that you've got different levels of luminosity or opacity. So the black regions are essentially water rich because water is almost opaque to IR, but ethanol is opaque, but not as much opaque to AR. So basically the lighter regions are possibly ethanol. So you can clearly see that you've got these segregation events taking place, and these are pretty random. I mean, they're pretty vigorous, I would say. They're definitely not at all symmetric. Definitely, you've got a lot of competition going on. Initially, you will find that ethanol would evaporate faster, and later on, we expect that it's the water's turn to evaporate. So we wanted to understand that carefully in terms of whether you have got a liquid, whether you have got a droplet, or whether you have a pool of liquid. So in the top, you've got a simulation which we did containing hexane decane liquid mixtures. And you can see that, and what I'm plotting is just mass fraction. You can see that, and in this simulation, from what I remember, probably one side is a hotter side and the other side is a colder side. So you've got a Marangoni flux already. You've got a thermal Marangoni put in, but of course, solitary Marangoni is also there. And you will find some segregation events happening. So we've got some key questions coming up. So the questions are basically for layers. Obviously, as they evaporate, what are the patterns? Why do we get the patterns that we see, okay, during drying or during evaporation? Okay, we wanted to understand that. And the second question we wanted to do about droplets is, if you have a droplet and if you have a contact line, how do these guys evaporate and what happens? Okay, what happens to the contact line? And the third question we wanted to ask, and that's why I put particles there, they seem a bit of a misfit, is if you look at most of the experimental work which is done, if you looking at these evaporation systems, people do use PIV a lot. And PIV means you've got these microscopic particles which are going around. We wanted to see what role can particles play, especially if you have within a liquid medium, which is obviously when you have these chaotic events that are happening here, the particles are also subjected to a lot of push and pull. So we wanted to see what happens at that point and whether we have to be careful when we use PIV or not. I'm going to come to that in a second. So therefore, I've got my talk lined up in terms of layers, droplets, and particles. So let's just look at layers. So it's a very familiar system here. It's a very similar system, just as Smith and Davis kind of a thing, wherein you got a liquid, but this is comprising of A and B. You've got two components, A and B, subjected to within two walls. One is heated up and the other one is cold. So you've got a horizontal temperature gradient, and that results in a thermal Marangoni automatically. But because you've got two different components, you will have a solitary Marangoni as well. So, and one of the things I must confess immediately in the beginning is most of the work which we have done have assumed that it's an ideal mixing rule. So basically, we've got arithmetically average mixing rules. Of course, I mean, if you consider some of these mixtures, especially when they approach azeotropic compositions or things which are very non-ideal mixtures, all of these will go out of the window. So, but we are restricting ourselves to supposedly simpler systems where you have ideal mixture laws still applicable. Okay, so obviously you've got usual mixing rules for the properties. You've got surface tension as a function of temperature as well as concentration. So you've got both the thermal as well as solitary components there. And you've got the usual set of equations. The usual set of equations being you've got the mass balance. Forget about the red bits there. I'm going to come to that. You've got the color equation or the interface equation. You've got the momentum equation. And obviously, if you have different components, you will have you've got gradient of temperature accounted for here. This is the surface tension gradient for temperature as well as for concentration. You've got energy equation because you're heating it up, you're heating the system up. And if you have evaporation, you have a evaporative flux. This is the red bit. So this is the evaporative flux. Very simple. And again, in this evaporative flux, we are assuming slow evaporation. So that means that we can assume normal vapor liquid equilibrium, like Raoult's law. So we are using extremely simple system, extremely simple formulations here to avoid any kind of ambiguity. Okay, and if you have evaporation, obviously you will supply the vapor phase with the most volatile component. So you will have the advection diffusion within the vapor phase as well. You will have the loss of the component within the liquid. That's also accounted for. So you would have all of these. So essentially, these are the usual set of governing equations that we'll use within the DNS. And then these are typical Smith and Davis type of boundary conditions. Nothing really specific there. You've got a base state velocity, plus you've got the thermal gradient. You've got the you've got the zero flux conditions at the top and the bottom, set temperatures at the walls. One is hot and the other one is cold. So you've got plus half and minus half on the two sides. And that's it. And when we go ahead with this, what we have is basically you will see the evolution of these so-called, I've used the word hydrothermal waves because they're used usually in literature. But for me, they're basically thermocapillary or solutocapillary waves here. And what you will see is you will find these patterns that are developing. You will find these patterns developing, and you'll see a certain angle. And we find that, well, if you consider a pseudo single component, we do predict what Smith and Davis predicted. So at least for the pseudo single component case, we are predicting what Smith and Davis predicted in 1983. So which is okay. Okay, but if you look at the saturated, if you look at the case where you have hexane and decane, and if you just take a slice, you will actually see, obviously you will see temperature fluctuation, you'll see velocity fluctuation, but importantly, you will see mass flux fluctuation as well. And you can see that some areas are richer in some component than the other. Okay, so there is some segregation which is being seen. Obviously, this is just a quick test for that. So we wanted to understand this a bit better. So we did a full stability analysis for this. So what we do here is we look at a layer, and what we are doing is we are doing a quasi-steady stability analysis, and this is okay because we are looking at slow evaporating systems. Okay, so therefore we can freeze the stuff in time, and we are able to actually look at what instabilities are kicking where and things like that. And obviously, the moment you have a binary liquid system, it's a spectacularly rich system. And it's rich because you've got latent heat ratios. You would have things like latent heat ratios because each of these components will have different latent heats. You'll have molar ratios, you'll have vapor pressure ratios, you name it. You have a density ratios, surface tension ratios, and so on. So this is a very, very rich problem. And obviously, because you've got two components here, you will have the solutal Marangoni, and this is how we define the solutal Marangoni. So it's sigma A. There's a surface tension of one component minus the surface tension of the other. This is how we have defined it. So wherever you see negative Marangoni number, that's because surface tension of one of the components is greater than the other. So it doesn't. It's not a non-physical scenario. Okay. And you've got thermal Marangoni here as well. And obviously, this is the important thing. We define the evaporation rate as some ratio between the temperature difference versus the latent heat. So it's something similar to a Jacob number or a Stefan number or whatever you may want to call. Okay, and obviously, one of the important assumptions we make here is because this is a slow evaporation case, we're using the Hertz-Knudsen evaporation laws. So basically, we're using the same evaporation fluxes based on Hertz-Knudsen rule. And over there, you will have a non-equilibrium parameter, K, and that's defined as that. So this is basically the summary. This is basically the problem setup for the stability. Okay, so usual set of equations here. We are looking obviously in the 2D system, and then we'll have a base state, and we do a quasi-steady stability analysis on this. Okay, these are the typical boundary conditions on the interface. You will have the mass flux, the evaporative flux. So you've got this mass flux over here. This is evaporation flux is defined here. This is very important because each of the components has a different evaporating flux. We have also accounted for that. So one of them may be more volatile than the other, and that's the reason why we did that. Okay, and of course you'll have the energy balance. You'll have the tangential stress balance. Nothing really spectacularly different here. Normal stress balance in the usual methods. This is basically A is the Hamaker constant and things, especially when it goes down. But we know that we really stop the simulation. We really stop our analysis when it really gets low. So we are looking at the initial. We are looking at how the patterns are generated. So we are not really going into the element of drying perspective. You still have a film. Okay, and of course, yeah, you've got the energy equation, you've got the concentration equation on the interface, and so on. So there's nothing really different in this. And of course, surface tension changes with respect to concentration as well as temperature. Some of the values. So we are relying on water-ethanol mixtures. So our dimensionless parameters are basically representative of water-ethanol mixtures, and we are looking at quite thin films here. So we are usually in the range of microns. So in this case, I'm going to be presenting for the ranges of around 1 micrometers, and that's what I mean. These are the traditional. These are our usual dimensionless numbers that come across. So once we do that, once we evolve the system in a long wave approximation, I'm just presenting the final equations because I'm going to be talking about other things as well. So so you'd see that you got this is how the height would change with respect to time. You got various terms. You've got all kinds of terms here relating to vapor recoil. You've got thermal Marangoni, solitary Marangoni. You've got surface tension, disjoining pressure, and evaporation. So you've got the whole gamut of physics that is going on. Similarly, we'll have a concentration equation on the interface as well, which will have components pertaining to surface tension, similar components pertaining to solitary Marangoni or thermal Marangoni and things like that. Okay. What we're going to do is we're then going to do the quasi-steady analysis, and we put this perturbation in. We plug in our equations. We have, obviously, all of these equations will transpire into their own terms. Nothing really great in that. And then once we do the frozen interface approximation, we'll get a growth rate which looks like this. Okay, so R is the growth rate, and if R is completely real, the real part of, if the real part of the growth rate is positive, it's unstable, and if it is not positive, it's going to be a stable system. And this is the important bit what we have to look at. This is basically where the discriminant is. And obviously, if the discriminant is positive, then you got the entire growth rate is a real number. And in that case, what we have is we have got a different set of, we call that as a monotonic instability. Okay, I'm going to come to the solutions soon. And if the discriminant is negative, you have a complex system here. And then if you have a complex system here, we normally are within the oscillatory instability mode. I'm going to show you how these transpire very soon. Okay, so I did mention about the equilibrium parameter K. So when K equal to 0, it's the so-called quasi-equilibrium parameter where it means that the temperature of the interface is having the same temperature as that of the vapor, and the temperature of the interface is not varying at all. It's a pseudo system. It's an equilibrium system. So in those cases, if you suppress the evaporation rate completely, so if you suppress evaporation completely, you'll find that the system is completely stable. There's no real instability kicking on. And if you have a small evaporation rate, then you will find that the system is unstable. But however, we are never under quasi-equilibrium. So we're going to look at K not equal to 0. The thing is, if I put K inverse as equal to 0, that is a completely non-evaporating case. So we are not even looking into that. Okay, so this is the interesting bit. So wherein you've got a non-equilibrium scenario, what we'll find is you'll find that there are two. What we find is there are two distinct modes. One is the monotonic instability, and the other one is the oscillatory. So oscillatory is when this whole guy is going to be complex. Okay, and what I'm going to show you now is how these transpire. Okay, so what is a monotonic instability? So a monotonic instability is when you've got B, which is less volatile than A. Okay, so A is evaporating faster. So if A is evaporating faster, the concentration of A is depleted in the trough of the wave here. But then this is because this is subjected to a heated wall. So this is going to evaporate faster here. So this means that the concentration of A is going to deplete faster over here, but the concentration towards the crest is going to be positive. So you're going to be having a kind of a pull. You've got a solitary Marangoni towards the positive side, towards the crest. And the same thing happens. You've got a high temperature here. You've got a high temperature here because it's closer to the wall, and low temperature here. So you again have a thermal Marangoni going in the same direction. So in a monotonic instability, you've got the thermal Marangoni and the solitary Marangoni collaborating with each other to develop your patterns or to develop these waves. Okay. Now, if you consider the oscillatory instability, it's a complete reversal of fortunes here. So in this case, B is more volatile than A. So B is more volatile than A. That means that the concentration of B is going to be depleted, which means concentration of A is being enriched here. And obviously it's less over there. So concentration of A is enriched over here. So that means that the soluto capillarity is actually pulled towards the trough. But on the other hand, the thermal marangoni is not going to change. You've got a high temperature and low temperature over there. Thermal marangoni is going to be pulled over there. So you've got this constant push and pull going on, and which is what we call as a solutal, which is what we call as a oscillatory instability. How do these transpire? So we did a lot of parametric analysis across a range of parameters, across different. Alpha is the ratio of the volatilities, and basically you've got the ratio of the solutal versus thermal marangoni, and we have mapped under what system, under what circumstances you may have a oscillatory instability or a monotonic instability. So we find that obviously if you keep increasing your evaporation rate, you actually increase the region for the oscillatory instability. So you can see, well, you actually increase the region for oscillatory instability. Okay. So how does this transpire? So we did simple, very simple simulations here, numerical simulations. So here, what I'm showing is this guy is basically showing the temperature, how temperature changes with respect to the height. So this is how the height is. And you can see that it simply is a very simple kind of it's a monotonic. So everything is being pulled towards the crest, or it's pulled the other way around. So there's nothing really fascinating happening here. Okay. But in case of an oscillatory instability, so this is the region where where there's a constant push and pull in opposite directions. So you'll find that you'll have a very rich dynamics which appear. Just a few more seconds, and hopefully you can see it. You've got it's taking its time. Yeah, things are happening now. So you can see that there's a constant push and pull. So the pink line is basically the height, okay, and the green line is how the temperature varies. This is again the height, and this is the zoomed up version of how the concentration is. So basically, so obviously you will see this rich pattern over here. This is again represented here. And what we think is definitely is if you have a binary mixture system, you do get, you will obviously have all kinds of combinations of thermal and solutal effects. Some of them which can lead to monotonic kind of patterns. You may have a puddle or you may have a mound, but in some cases you will have these patches everywhere. So possibly they may be because of the oscillatory instability mode. Okay, so we did all kinds of things. We analyzed this in the non-linear regime. We checked it. We looked at how the interface height and temperature, as well as the concentration vary. And by looking at the growth rates, we could easily find that essentially the whole system is fully enslaved to the soluto-marangoni instability. So we could also see that. Okay. So this has been published in PR Fluids recently, and we are doing further work, and I'm going to come to that soon. So the next part of the story, is about sessile droplets. So here, so we have looked at the layers where you've got multiple or binary components there, and now we are looking at droplets with binary components. So again, we'll be looking at, I mean, the first, I'm going to today concentrate on volatile or liquids. Okay. Volatile liquids. We have also done some works on salt, and I'll see what I'll see how much time we have. So again, we've got the same system. We've got the same, very similar kind of an approach. You've got a droplet, but this is an important assumption we have made here is this is a flat droplet. So essentially it's sitting on a hydrophilic substrate. So it's a very thin droplet. So that we can employ a long wave and other approximations and things like that. Okay. And once we do this, we'll apply the lubrication theory. we'll have the same set of, nearly the same set of parameters. You'll have a thermal Marangoni, you'll have a solutal Marangoni, and so on and so forth. You'll have very much similar set of equations there, nothing really different. So you can see that you've got thermal as well as solutal Marangoni here. Okay, similar set of boundary conditions on the interface. Again, you will have an energy jump condition, looking at taking into account different evaporative fluxes for both components A and B. And again, we are employing the Hertz-Knudsen here because we are looking at, again, slow evaporating systems. So I'm very slow evaporating systems as well. Okay, and we are now comparing against experiments as well. So this, we had access to experiments at this time. Okay, so again, you've got a concentration balance. You can have an assumption of rapid vertical diffusion. That means whatever is in the bottom of the stuff is just going to rapidly flood the whole system. But of course, most of our systems are going to be having weakly diffusive systems within the liquid interface. Within the interface. So, so most of our results focus on the weak diffusion approximation. Okay, we have these sets of initial conditions. We have a precursor layer for obvious reasons. We want to make sure that we had to make an assumption that the precursor layer is non-evaporative. So JA, JB is both set to 0. But of course, most of the evaporation takes place within the droplet. Okay. Again, ethanol water systems, typical values we are using. And the reason we are using this is because we have also done experiments, so it's easier to compare. If you look at pure water is a bit boring. So you have nothing there. You've got simple evaporation of the water droplet. You got maximum mass flux very close to the interface, very close to the contact line. Nothing surprising there. Surface tension, yeah, you would have a small gradient there. That's set up mainly because of temperature. The moment you have 10% ethanol, you've got something very interesting happening. 10% ethanol, you have a massively faster evaporation rate, obvious, because your ethanol is more volatile. But at the same time, if you look at the contact line, you've got a massive amount of spreading that is occurring with respect to when you have a 10% ethanol system. Okay, again, we have looked at this very closely. We have looked at it for various concentrations, 10%, 50. I think we went up to 50% actually, both experimental as well as using a model. When we discretize our velocities completely, when we actually decompose our velocities, we can see that it's basically the solutocapillary velocity, which is the culprit, which enhances spreading behavior. Okay, so it's very clear that it's basically driven mainly by the solutocapillarity. And we also compared with, these are, we are not comparing apples and oranges, we don't want to, but we find that we have a similar trend, at least the lifetime of the droplet trend, very similar to that predicted by heptane and octane data, experimental data. And this is, our simulations are basically this. So that the trends are similar, but we are comparing against our own simulations. So comparing against our own experiments, sorry. So this is our experimental setup, a very simple setup, wherein you have a glass slide and you've got a heating pad, and we just put a droplet of water. And we look at, and these are specialist slides wherein we have make sure that it is hydrophilic in nature, so that we can have a flat droplet. Okay, so this is what your water droplet looks like. So simple, nothing really spectacular. You've got a small spreading rate, and we can see that the spreading rate is very similar as well. This is just for water, and you can see that the substrate is heated to about 70 degrees Celsius. Okay, nothing really dramatic here. This is 50% ethanol, and you can clearly see that you have a immediate spreading event. So you've got a ridge which is there, which keeps spreading, and that's because the ridge is rich in ethanol. As it evaporates, obviously, as ethanol evaporates off very quickly from the edges, it keeps spreading. But then the moment it's all lost, it's completely rich with water. Water has a higher surface tension, and everything is pulled back. Okay, so you've got a spreading rate, and as well as you've got a retraction rate. Okay, so we have compared both of these, and they look pretty good in terms of comparison. So one of the learnings which we have made here is that definitely if you have ethanol water mixtures or binary mixtures wherein one is more volatile than the other, you would have spreading events, and we have, and other many authors have also seen that as well. Okay, so this has recently been published in JFM just about last year, I think. So you can have a look. What we are now doing is we are also looking at the quasi-steady analysis of a droplet. And this is done by my recent student, Katie Thompson. So what she has, along with George Karapetsis. So what we have done is we've looked at obviously a binary droplet system, and we did again a quasi-steady stability analysis, and we found that it doesn't really suit. Okay, and I'm going to explain why. So if you look at, if you do a simple quasi-steady analysis for a droplet, we can see that the most unstable mode really matches. I mean, this is a pseudo single component. It matches very well with what others have predicted. It's fine. We really have a good match with the most unstable mode. This is a simple dispersion curve. Okay, but the moment we have another mixture, another component, you can see these numbers. These are very, very high growth rates. Okay, and of these, obviously, this is the maximum most unstable one from the resolution that we have. And obviously, we know that if you have so many modes which are active, I'm not really trustworthy of what information QSSA would give. So actually, at the moment, we are actually doing a transient growth analysis for these droplets. So hopefully next time, or probably in a couple of maybe next year, I'll be able to show you some transient growth results from our droplets. Good. So again, yeah. So recently, hot off press, this has just come out yesterday. We have also done some work in terms of looking at droplets enriched by hygroscopic salts. So these are lithium bromide salts, and lithium bromide is a nasty salt because it's actually as hygroscopic. So it actually sucks off. It will suck off water vapor from the atmosphere, and we find that there is always a tug of war between evaporation and absorption in this case. So I'll leave this to some other day because this has just come out. But so we have also done a similar we have used our similar principles, but we had to completely modify our thermodynamics to make sure that we are able to represent salt solutions in this paper. Now, the thing is, when we look at any of these systems which are highly volatile, whether it's layers or whether it is droplets, many of my colleagues would use PIV to understand what is the motion within the droplets or within the layers. But my question was, will these particles, because obviously these are particles, these are small particles, will these particles ever affect the flow? Okay, especially when you have actually already seen that if you have a binary mixture, and if you have a binary mixture which is evaporating, you will have segregation events that are going on within that. And if you have particles within it, would that disturb the system, or would it really represent, would it really do the job what a PIV particle would do? Okay, so that was the question we began with. But then it's obviously a general question as well, that just how, if you have a non-spherical particle, how does it behave in a fluid? So we did a lot of, so what we did is we digressed a bit, and we looked at, first thing is we looked at inviscid systems. Now for inviscid systems, there is this old paper by Kozlov and Onyshchenko, it's in Russian. And as with all of these extremely informative Russian papers, just 4 pages would do is they would start with, we know that. And obviously it was a very, very difficult to read paper. So it says that basically the Kozlov-Onyshchenko theory, it says that if you have a general ellipsoid, the general ellipsoid can only show chaotic motion, like a tumbling motion, chaotic tumbling motion, only under a few conditions. The conditions being that it should have basically all of its axes must be different. So A should not be equal to B, should not be equal to C. The moment you have a kind of a spheroid wherein two of these axes are the same, you will actually destroy the, I mean, you will not have chaos anymore, or you'll have less chance of having a chaos. So just to explain it well, I'm not sure if you can see from the camera. I'll try to show you. So if this is kind of a solid, it could be of any arbitrary shape. Essentially, what we are doing is we are living on the solid and we are seeing how exactly the solid actually moves. So whether it's going to move in a very periodic fashion as it traverses into the domain, or it's going to tumble in a very chaotic fashion. Okay. So that is the question I want to see, because obviously most of our PIV particles, we prefer them to be neutrally buoyant and things like that. So over here as well, we look at neutrally buoyant particles. We define a density ratio as rho fluid versus rho s. Okay. And then we can give an initial kick to the particle. So essentially, if you have this particle, you can either have a translational or you can have a rotational kick. You can give it in any way you want. And obviously, that means that you can have a large number of initial conditions represented by this set over here. Okay. And what we also do is we actually have a point marker to identify how exactly, if you are living on the particle, we are just tracking how many times would this point actually come back to the same position, okay, to see if it is periodic or if it is chaotic. Okay, so we look at the general ellipsoid. We have it's basically in a simple rectangular domain, periodic in every side. We can have a generalized Reynolds number based on the diameter of the particle. That's not a big deal. This is the important thing. You've got the initial kinetic energy ratio. So it's basically the translational kinetic energy versus the rotational kinetic energy. So this is I is the moment of inertia, and omega is your angular momentum and things like that. Okay. And what we used for this is basically Jerez. So this is where we had a lot of intensive collaboration, intensive work with Stefan Popine and Zaleski. So obviously Jerez is there, a usual flow solver, but obviously they didn't have a solid solver. So we developed a solid solver for that. And that's now open sourced as well. So you can have a look at it if you want to. So what are the equations being solved? Usual equations, nothing really dramatic here. You've got the mass conservation and you've got the momentum equation here for the fluids. F is basically the force on the particle or the solid, okay? And that F is obviously acting on the entire area of the solid. This is obviously coupled to the solid governing equations as well. You've got Newton's laws, essentially, nothing really great. So you've got translational momentum as well as angular momentum. And if you have contacts, if you have multiple particles, we also have a contact and a force field approach as well, a contact model as well as a collision model as well. So I'm not really going into multiple particles. That is for a subject for another day. But I'm going to focus on a single particle and what can lead to chaos in that. Okay. So obviously that is the numerics part. We also wanted to check whether our numerics are really making any sense. So we looked at Kirchhoff's equation. So this is from traditional Lamb's book, Kirchhoff's equation. So you've got the total kinetic energy given by angular as well as the translational one. So that is the total, and if you see this in these Kirchhoff's equations, you'll see that this becomes a Hamiltonian. So we also did a lot of Hamiltonian dynamics and evaluated the torque and also the force, and looked at what path and what are the conditions of chaos and things like that. And I'm going to present some results on that. So the first case we're going to do, this is the actual simulation. So this is a case which is non-chaotic. So you can see that the solid is just tumbling normally. And on the side, on the right over here, you can see what we call as a recurrence quantification plot, usually used for chaotic systems and stock markets as well. So essentially, so what it says is, if I have set a marker point here, and if I say that, oh, whenever this marker point comes to this point, plot a dot. Okay, it'll plot a dot. And obviously, if it's like a periodic system, just rotating in a very, very simple way, so we'll have it'll constantly plot these dots in a very straight line as time goes by. So that's what it's showing. So this is a very, very periodic system. It's a highly non-chaotic system. And here the energy ratio is pretty low. So the extent of kinetic energy versus the angular energy is pretty low here. In this case, if you increase that, you will see that the object tumbles pretty chaotically. I mean, it has no control on what's doing. And if I look at if I really look at the recurrence quantification plot as well, it has a beautiful fishbone type structure. And this structure gets more and more complex as simulations go. So basically, you can see that you have a chaotic element, and one of the things is identification of chaos is such a field on it to itself. So we employed RQ, these recurrence plots, as well as other methods, the statistical methods. But at the same time, we also used our own Kirchhoff's equations to actually plot Poincare maps and things like that. Okay, so these are some of the results. So obviously, RF and Jones attribute to RF as well, who was a pioneer in this. So for a non-chaotic case, you can see that the orbit that is tracked is fairly circular. So we also get a completely circular shape, circular track. And our Kirchhoff's equations, they also predict a very, very periodic path. So this is essentially, if you remember in my schematic, you had a marker point M. So this is the position of the marker point M. And we use the same position to our DNS as well. But the moment we give high energy to the system, you can see that this is a complete mess. Okay, and we do get a complete mess as well in terms of our simulations and in terms of our theoretical calculations as well. So we were really pleased with this result, because this is a very, very difficult problem, especially for making sure that validating our simulations. But one of the important things that came out from this, not only validation from the theory, is that I'm going to tell you a secret later on, but it's fascinating. So we did, of course, we as usually everyone would do, is we just wanted to see, is there really a region where you can find chaos, or is it like limited to a certain region? So when you keep increasing rho, that means as you make lighter and lighter solids, your system, and obviously this is for inviscid systems, yeah. So we'll come to viscous systems, because we are looking at viscous systems as well. So you can see that there is a small range wherein there is a range where things are chaotic, and we confirmed these points using Poincare maps. Okay. And what we did was we wanted to check whether our DNS also predicts the same thing. So what we did is wherever you see these circular symbols engulfing this thing, that's where we have done DNS as well. So we can see that some of these our DNS also captures a very similar behavior. But in case of DNS, we were actually torn between. So if you have a chaotic behavior, these dark circular points, and if you have a purely periodic behavior, these dark squares, we could find some place. We could find a region, obviously, where it's not really periodic, but at the same time, I can't really call it chaotic as well. So we call them as quasi-periodic. So this is the region where you may have some quasi-periodic systems. So wherein your point, it's not actually going around a full circle all the time, but it's nevertheless, it's just retaining the circular shape. It may form, I think I can show you an example. So this one over here, it's not just plotting the same line again and again and again, okay? You have some differences, so we can say that this is possibly a more quasi-periodic system. But then other quasi-periodic systems, you could really see that they retain that motion, but they may have a larger region. They may have a larger region as well. Okay, so now what happens if you have viscosity? So obviously, when you do PIV, especially within a droplet context or anything, you do a PIV, and and as we saw in the previous things, you have all kinds of forces that are acting here. You've got thermal Marangoni, you've got solitary Marangoni, you've got heat transfer, you've got buoyancy, and all kinds of stuff. So obviously, the object is experiencing all kinds of hits and kicks from all over the place. Okay, so what we did was, in these simulations, we also introduced viscosity, and one of the important things I mentioned earlier is from the Kirchhoff's or Kozlov's and Onischenko's theory is that if you have B equal to C, if you have a spheroid, in an inviscid case, you will most likely get a periodic or a quasi-periodic orbit. But when we put in viscosity here for a spheroid, okay, we found chaos actually. So the thing is, and the reason we found chaos is when we do the full analysis of our equations, and if we look at the added mass tensor and things, added mass tensor and angular momentum and things like that, we found that one of the integrals of motion, which is, so if you have B equal to C, the integrals of motion in the other direction, which is A, is causing the chaos in viscous systems. So and that is actually observed through these vortex shedding. So you can see these asymmetric vortex shedding which is happening into this. So this was basically what we did, and this is now published here in recently. So what we are now doing is actually putting, obviously when you do PIV and any kind of a system, you will have multiple particles. So we are looking at how these multiple particles actually interact with each other. And do they collaborate to develop chaos? Or do they don't really collaborate with each other and they're just periodic? Will they dampen the system to periodic systems, or will they actually accelerate chaos? That is the question which we want to see. So my new student, Andrew, is working on that. Okay, so very quickly, summary. I don't know what time is it. Yeah, we got 10 minutes, so thankfully. Yeah, so very quickly, the summary is, obviously for pools, we could find out that you got the flow structure, which is strongly dependent upon the solitary Marangoni or the thermal Marangoni systems. We can be either monotonic or oscillatory. In case of binary drops, obviously we found this interesting spreading behavior and retraction, again driven by solitary Marangoni. And basically, the question we want to still answer is what modes really dominate. Okay, and so that's why we are doing this. That's why we are doing a transient growth analysis through Katie Thompson. And again, when you have particles, we want to see what is the collaborative. If you have more particles, will they collaborate with each other? We want to find out. We want to find out more about it. Plus, at the same time, we can see that obviously even in a viscous system, you can have chaos generated because of vortex shedding. Typically in viscous systems, one would expect chaos to be suppressed, but of course, if you have weird added mass tensors, and if you have weird directions, then obviously that's not the case, and that's what we found. But then the question we want to see is, if you have a pure fluid, and if you're doing experiments using PIV, you're fine. But then if you're doing binary mixtures, and if you have these particles all over the place, you don't want to remix those particles in the segregated system, because essentially segregation is what thermodynamics favors, and particles may actually bring them back. So we want to check really if you have multiple particles, whether there's a collaboration or whether they just behave as, whether your PIV will just show what your PIV should show. So with this, I'd like to thank you for listening, and I'm opening the floor for questions.
Great, thank you very much, Prashant, for a fascinating talk. And yes, we have plenty of time for questions. Christo, you have a question. Christos Markidis.
Thank you, Dimitri, and Prashant. Nice to see this, and actually really nice to see this for the first time. I don't think I've seen you go into the details of this before. I have a comment and a question. So my comment was at the last conference on international, the boiling and condensation heat transfer in Japan, you were there. I asked 3 people, 2 of which were experimentalists and 1 of which was a modeler, whether we should go towards smaller particles or larger particles when we're using PIV in these types of flows that you're showing, right? So droplets, interfaces, all the difficulties that you've spoken about. and I got 3 different answers. So I'm really happy. I'm really happy that you sort of embarked on a journey to try to help us a little bit understand, what we should be doing experimentally to measure these flows properly, because they're difficult. They have these challenges that you mentioned. My question is as follows. You posed the question initially, and I should maybe clarify that you're dealing more with not the case where the particle is interacting with the contact line. So
Yeah, no, I'm not even getting
with
that.
with the internal flow in the bulk due to a vertical. My question to you is as follows. The problem that we typically have isn't to pose the question that you posed, which is, does the presence of the particle affect the flow? Because the answer is always yes, but to a larger or smaller degree.
Yeah.
So I guess the real question for us, and I don't know, this is where the question comes in for you, which is, how can we use what you've done, which, there's a lot of stuff there. How can we pull out useful lessons for what would the errors be in different cases, and turn it into a little bit of a manual for experimentalists, right? So, use these types of particles. What's the difference between small and large particles? You already started talking about shapes, right? So you've given us some insight there.
Yeah.
In terms of, how wrong can we be here, right? I mean, is it just a little bit, we can just forget about it? Or is it like, okay, you're measuring something completely different?
Yeah, so a very good question, Christos. So I think it's a very comprehensive question. So about these particles, I think if you're more or less like a spheroid, and if you're more or less have a spherical shape, and if they're as small as possible, I think they're better, because they would not really have this added mass enough to really disturb the entire thing. But the main issue comes is if you have these irregular shaped particles. And of course, what we still don't know is, we want to do ourselves is, what happens, obviously, when you do PIV, you're having many particles. And we want to see how these particles, if at all, we know that they collaborate with each other. We know that there is hydrodynamic interaction. There's all kinds of things that are happening between them. So we want to see how does that interaction transpire. So essentially, I would say lighter, smaller particles may be good, maybe better, but I think we need to still wait to understand when you have these high mass fractions. So I think if you have a number of particles, then my honest answer is I don't know at the moment. Yeah.
Thank you, Prashant. Thanks very much.
Yeah.
Very useful. Thank you.
Yeah. So what kinds of Reynolds numbers are we talking about for these simulations? The viscous ones.
Oh, the viscous ones, the ones which we did a range of Reynolds numbers, Dimitrios. So we did very high Reynolds numbers as well. We went up to, from what I remember, we went up to 10,000, but we also went to very low Reynolds numbers as well. So just to look at, I mean, we know that for low Reynolds numbers, you quickly dampen the chaos. If you have a single particle, you'll quickly dampen the chaos. It becomes a periodic system. So essentially, your PIV particles will behave as you expect them to. But the question is, even at low Reynolds numbers, we now know that what we expected, honestly, was that the moment we add viscosity, the chaos is going to die quickly. That's what we thought. But we didn't realize that the shape will have a huge role to play.
Mm-hmm.
And of course, so smaller is better, lighter is better. But again, the question we want to ask is, if many is better.
But what's the smallest Reynolds number you could get chaotic behavior for?
I think the smallest Reynolds number within the, I mean, obviously this is scaled with the particle size. So the smallest Reynolds number we could actually go to was about 0.1-ish. That's what we tried from the simulations aspect. We didn't go less than 0.1, but yeah.
And they did chaotic motions.
I mean, the thing is, it quickly dampens away. And ultimately it becomes kind of a regular periodic motion, or it comes to a complete stop. Yeah.
Oh. Okay, because I mean, it may be interesting. I think Hassan Arif did some work where they had more 3 particles, right? three particles settling in a Stokes flow, and they could get chaotic motions.
So in the paper we did some of those simulations to validate our numerics as well. So we looked at, I think there was a paper also by Hassan Aref's paper, as well as there's another paper by Lose, I'm not sure. There's another paper as well. So we have these. So they show that when they settle, they actually have a tumbling motion. So we could predict that as well at very low Reynolds numbers. So that was not a problem to get. And of course, those were perfectly periodic systems, so there was really low level of chaos there.
Good. Any other questions from anyone else? Just unmute yourselves or put the question in the chat.
I'm just opening my chat as well. Okay.
But I mean, it's interesting. I mean, I have no idea about the experimental aspect, but if you're doing PIV, presumably there's a lot of particles there, and you're probably averaging in some sense, right? So you may want to do statistics from the.
I mean, that's going to be so we just embarked on that, and one of the things we noticed was that the statistics become so complex. So my student Eric, he did something called as cross correlation analysis, which was I would say somewhat helpful, not very helpful, but we need to really understand it better. So very, very early days. Good.
Does anyone have a question, or shall I ask another one? I have another one. Going back to the evaporation of droplets. I remember talking to Steve Davis when he visited us a few years ago. He mentioned that at some stage during the evaporation, they were seeing 90-degree contact angles. So the angles were becoming very large. Do you see anything like that?
No.
I mean, I guess theoretically you wouldn't, because you're imposing.
We have a principle, but we never saw even the experiments what Adam did. I mean, they were. We did look at the data pretty closely, and we did not. I mean, at some points it became greater. I mean, we initially started off with around 30 degrees or so, and we could see some increase, but it didn't go to. I mean, especially when it retracted, there was some sort of an increase in the contact angle, but it never went to 90. From what I remember, it was up to 50-ish. So it never went. But of course, after that, everything boom evaporated. So just before. So that, I mean, we can expect that because you've got almost pure water at that point, and water is has less surface tension than.
Yeah. Great. Any other questions? So George Karapetsis was on the call.
Yeah.
So anything else? Any other questions?
Hi, George.
I'm here.
Good to see you,
Nice to
George.
see you.
So okay, well, if not, let's thank Prashant again for a fascinating talk. And
Thank you.
Just an announcement: next week's talk is by Uti Tamisola from KTH Stockholm, and she will talk about complex flows, simulations of complex flows.
Brilliant.
So kind of staying on the same aspect. Okay, well, thank you very much again, Prashant, and Have a great weekend, everyone.
Thanks a lot, Demetrios. Thank you.
Thank you. Bye.
Bye.